Today we'll be talking about Attacknet. This is a brand new tool by Trailbits aiming towards testing consensus protocols and blockchain nodes. I'd like to give a special thanks to the Ethereum Foundation for co-funding the tool. This is interesting because it's a very different way of testing a blockchain node compared to like what you might be used to in smart contracts with like a fuzzer or static analysis. And to give you like a little taste of what we've got coming, we were able to use this tool, and while testing it, we were able to reproduce the finality incident from last year that happened on Ethereum mainnet. Before we get started, though, a little bit about me. My name's Benjamin Samuels. I post on Twitter sometimes. If you want to follow the Trailbits blockchain team, you can do it right there with the QR code. Trailbits, if you haven't heard of us, we help developers build safer software. We also maintain a couple of tools that you might be familiar with, Slither, Echidna, Tealer, and a couple of others. Before we talk about Attacknet, though, we have to talk about the state of blockchain node testing. This is going to kind of echo some things from the previous talk. So blockchain nodes, they're very similar to like a Web 2 backend. They have, they're going to have basic bugs, they're going to have implementation flaws, and the normal way to handle that is, you guessed it, like unit tests, parameterized tests, different types of tests that you write. But blockchain nodes also tend to have a specification, which is very helpful for more advanced testing. So there's multiple clients in Ethereum, so you can do differential testing. You can test two clients on the same network and be able to find bugs in either client, and that's really, really, really powerful. And finally, we have like a bunch of these like real-life issues. So you've got like issues with the specification, you've got like denial of service resilience, all these negative externalities and stuff that you basically can't write tests for. If you did want to write a test for, it'd be really, really miserable. And so the way that we handle this is with testnets. So testnets, what is a testnet? A testnet is just a public, valueless blockchain that is deployed in real-world conditions. Usually it's running like the next version of the hard fork or something, and we're using this to try to work out and detect all of these issues ahead of time before they hit mainnet. And testnets are really good at what they do, but they do have some limitations. Some of the real-world faults that happen on mainnet are not common or predictable. So imagine like a BGP hijacking attack, or maybe like a third of the internet goes offline because of some routing issue, or there's latency that gets introduced and taken away really fast, and like no one ever knows about it. And the other problem is that the conditions on the testnet aren't always representative of mainnet. And this can be improved over time, but it's kind of like one of those unknown unknowns. You don't know what conditions are important to reproduce on the testnet until you run into an issue on the mainnet, and you're like, okay, well now we have to reproduce this on the testnet because it's clearly something important that we need to test for. So that's kind of where the idea for Attacknet came from. The idea is, what if we took a DevNet and placed into like a clean room, like a sanitary operating environment? And the way that we would do that is we'd use a tool called Kurtosis. If you haven't heard of Kurtosis before, it's basically Helm but better. It makes it very easy to deploy testnets, or not testnets, but like devnets, like private devnets. It's very useful. They have a talk that's going to happen tomorrow. I highly recommend going to it. And so we're going to use Kurtosis to build these private devnets into Kubernetes. And Kubernetes is valuable here because we can arbitrarily scale to as many nodes as we need. And we also get a bunch of control benefits. We can do a lot of things to a set of Kubernetes pods that would be a lot harder to do if they were running on native hardware. And then we're going to inject faults into this DevNet using a tool called Chaos Mesh, and this is where the chaos engineering chaos testing comes in. We'll talk about that in a minute. And then once we inject these faults and the faults go away, we have to figure out if the network failed. So did it lose finality? Are there nodes that are unrecoverable that aren't syncing? Did any nodes get knocked offline? All kinds of different bad things that could happen in the network. So let's talk about chaos engineering. So chaos engineering is this idea from Web 2 that you have like a backend service, like Netflix has a backend service that serves content to its users. And they want to test that if something like the authentication service for Netflix goes down, it doesn't impact content delivery. And it's very hard to write tests for that in the real world. So what they do is they have a tool that goes around their backend and randomly kills services, kills pods, and this happens in production, so on real services in the real world. And if the network goes down, then it's something that has to be addressed systemically by whoever maintained the service that caused the outage. And so what we do with Chaos Mesh is it's basically a tool for introducing those kinds of faults. So we can do all kinds of crap. We can introduce network issues, we can do packet loss, corruption, packet duplication, we can arbitrarily kill nodes. We can do all of these things that should be tested on a testnet, but because the testnet is deployed globally, it's very hard to get in the middle there and introduce latency across half a network or something like that. So we really do need a clean room to do this kind of testing. So I want to go back to the May 11 Ethereum finality incident. If you're not familiar, basically in May of last year, a node was emitting stale attestations on Ethereum mainnet. And because those attestations were stale, a bunch of clients had to spend many resources to validate those attestations. A bunch of nodes, their memory use exploded and they went offline, and the network lost finality for a few epochs. And this was really bad, because this is something that you would expect a testnet to be able to address, but it didn't detect it ahead of time. And so testnets didn't catch this. One of the issues why they didn't catch it is because it required a large deposit queue. This issue just didn't show up if you didn't have a large deposit queue. There wasn't enough load on the network. Something else is this might have been a malicious attack. We didn't really have any way to verify whether this would be a malicious attack or not until we could actually figure out why was one of these nodes emitting stale attestations. And the last thing is, this could have been a misconfiguration. And misconfigurations aren't necessarily explicitly tested on testnets. You don't know what the misconfigurations are going to be ahead of time. You could think of some, but there's probably going to be some unknown unknowns in there, especially as the network evolves over time. So when we were building Attacknet, we wanted to try to see if we could cause the Ethereum finality incident without explicitly coding a node to emit these stale attestations. And the original Prism team write-up about it said the theory was you had the consensus client talking to the execution client. If they were disconnected for a period of time, maybe the consensus client would emit these stale attestations. And we tried that, and it didn't work. And so that was kind of disappointing. We weren't really sure at that point, okay, well, was this actually caused by a malicious attacker, or was it caused by something else? And so we decided to go through all the other Attacknet faults. We did memory pressure, we did all kinds of weird latency things, and we landed on this one configuration where if we injected a minus 10-minute clock skew on a Lighthouse Geth validator, and that clock skew lasted for 20 minutes, Prism node would start going offline. One Prism node would go offline from out of memory, and a couple slots later, another Prism node would run out of memory and go offline, over and over until all the Prism nodes were offline. And so this was a really cool result. But since the Prism nodes are going offline, the metrics that they emit aren't going to make it into Prometheus, and we can't actually look at them. So what we did is we spawned a new DevNet with basically infinite memory resources for these Prism validators. And these are the results that we got. So up here on the top left, this is a graph of the beacon head slot over time. So you're always adding new blocks as the slots progress, so it's always going up. The little yellow spot there, that's the start of the clock skew fault. So when that happens, the Lighthouse node's clock goes back from 9:10 to 9 a.m. And the Lighthouse node is like, well, there's stuff in my database from later than my current time. I don't know what to do. So it just sits there. And sits there for the following 10 minutes, waiting for the clock to catch up to 9:10 a.m. Until 10 minutes later, it catches up and it starts trying to emit attestations on the network again. And so it starts emitting these attestations, but keep in mind, its clock is still shifted backwards. And what we see is we see a spike in this replay blocks thing that Prism nodes call. And this is a very expensive function that's normally cached. But since the amount of time that has elapsed is long enough that it's not in the cache anymore. So all the Prism nodes are calling this replay blocks. And then we have one Prism node there who was scheduled to to propose a block. It sees this big memory spike. And when we tested this the first time, that was the first Prism node to go down. So this effectively proves that this probably wasn't a malicious attack. Most likely this issue wasn't even caused by like a disconnect between a consensus and execution client. It was most likely caused by a misconfigured NTP server, and that node started emitting these stale attestations, and it caused the Prism nodes to go down. Yeah, and so that's what we've got. So we can tell that the finality incident was most likely caused by this misconfigured clock, not by an attacker. Also, we weren't necessarily sure if this chaos testing method of introducing these faults was actually going to do anything or work. But I think that the fact we were able to reproduce this shows that this is a productive line of testing, and we should spend more time on it. There's also probably going to be other bugs that we can find with Attacknet. We're currently working on that right now. And if you happen to manage another L1 that doesn't use Geth, or if you made a lot of big changes to Geth, or big changes to Ethereum's consensus, you should probably run this too, because you're going to find bugs as well. And so that's what we've got. The tool is still being worked on right now. We're planning to do an open source release in December. It's going to be GPL v3 licensed, just like all the other Trail of Bits tools. You can follow Trail of Bits on Twitter to get an update when the tool is published. You can follow us on Twitter with the QR code. Again, big thanks to the Ethereum Foundation for co-funding this project. We wouldn't have been able to spend enough time on it without that. If you have any questions, or if you're interested in running this for your Ethereum client, feel free to email me. And yeah, that's it.